Unlike a lot of stuff that we've done, this project is sort of intentionally incomplete. We didn't want to just sort of come out and say, hey, look, we built this thing. We wanted to invite other people to come help build it along with us. So there's a bunch of missing pieces, some of them interesting, some of them maybe less interesting. But one of the things that I hope you get out of this talk is a sense that this is the kind of thing you wanted to be involved in. You're more than welcome to come help us along the way, and we can use help. So you're more than welcome. So first thing, this is actually going to work. Actually, yeah. About 2 months ago, Microsoft took basically all of the essential important code in the CLR and put it out open up on GitHub. And we call this the CoreCLR. And it's been there, it's pretty active. A lot of the work that people have done in the community is to help us port the CoreCLR to other OSs. Right now it only works on AMD 64. Pretty soon it'll also work on other JIT architectures as well. And the idea behind the CoreCLR is really to embrace the reality that at Microsoft, our Windows platform is a nice market and we're happy we have it and we have lots of lovely customers. But we realize that when people develop software, they want to deploy it on many other platforms as well. And we like our programming models, we like our languages, we want to encourage people to take advantage of the nice benefits they provide. This is a way for us to get our platform, our programming platform, available to deploy much more widely. So the initial ambition behind the CoreCLR is to basically help build people in server scenarios. We're looking really at ASP.NET, primarily running on Linux or Mac OS as a thing that you could use. So this is very active. It contains a complete and perfectly lovely JIT, which we call the JIT, or JIT, or exact pronunciation. But that JIT is a totally custom JIT. It's actually based on the original x86 JIT that we did long ago. It has a fairly baroque internal architecture, and even the people who work on it are kind of nervous about aspects of the code. And what we wanted to do is provide a way to experiment with code generation for .NET that was much more approachable. And so that's really sort of the genesis of the project that I'm going to talk about today. Before I get to that, in the CoreCLR, just so you remind you, or maybe you don't know, there's no interpreter. Everything gets JITted the first time it gets executed. There's no re-JITting. You get one shot at it, that's it. So the re-JIT, as I said, was in there. There's actually a pluggable JIT architecture, so you can overlay another JIT on top of the re-JIT and say, you get the first shot at JITting this method, and you can either JIT it or you can decide to pass. And if you pass, then the re-JIT will go ahead and JIT it for you. This makes for a really nice methodology for bringing up a new JIT, because in the beginning your JIT can't do very much, right? It's got a lot of missing pieces. Well, every time you hit a missing piece, you can sort of throw up your hand and say, sorry, I can't handle this method yet. You fall back to the other JIT. So you can still run realistic programs end to end. With the JIT is a nice thing because you want to push as much code through your JIT as you can. And then everything will still execute. The code that you do JIT will get run. You can decide whether it's correct or not and go on from there. So we'll take advantage of that in our thing. There is the ability to do what we would call install time code generation, or we call it NGen or cross-gen. So you can pre-JIT all the methods in an assembly and have that be something that can be installed and used instead. We don't have support for that yet in our code. That's one of the things that people could come and help add in. It's hopefully relatively straightforward. And then there's an interface between the JIT and the VM. I probably should put the word interface in quotes. As you guys probably know, anytime you have one group that controls both sides of the interface, the viability of the interface as an abstract thing becomes kind of questionable. So in this case, there's a ton of details that have sort of penetrated through both sides. And it makes implementing a JIT rather tricky. In fact, if you didn't have an example of a working JIT, it would be very hard for you to just use the interface and that specification of the CLR and the ECMA spec to figure out how to correctly do this. But we can fill in most of those pieces for you. The big complications come up with garbage collection and exception handling. This talk is mostly going to be about the implications of garbage collection. It wouldn't shock me if 6 months from now we go to the LLVM conference in the fall and we talk about the complications of exception handling, because they're both fairly complicated areas. So, you know, when I gave this talk at Microsoft, I actually had to explain to people, this is what LLVM is. I think I will go into it much. You know, we like what we see. Some of you may know we worked on a framework at Microsoft for a long time called Phoenix that in some ways had similar ambition to LLVM. In fact, Chris was an intern of ours long ago, back when I was on the project. And I think, you know, we're really happy to see somebody be successful in the space, because there's a clear need in the community for something like this. And it really makes sense for everybody to sort of collaborate together on one good framework rather than a bunch of diverse sort of scattered about frameworks. So we like what we see, we're happy, we're excited about becoming involved in this. I think you'll see increasing interest from Microsoft and LLVM as sort of time goes on. We still have our own compiler technology. We may or may not decide to make that be more open. It's sort of open for discussion right now. We'll see where it goes. But one of my hopes is that we can take some of the ideas that we had in Phoenix and at least sort of bring them up for discussion in LLVM as possible areas for pushing forward. A little hard for me to do because the projects have been secret for like the past 6 years and we haven't written anything or talked about it in public at all, so we still have to sort of work out those details, but we'll figure it out. So the project is now called LLILC. It stands for the LLVM-MSILC compiler. We have our site up there. We pronounce it as LILAC. And like I said, the initial focus is bringing up a JIT. It's not really our ultimate ambition to build a JIT, partly because we're not super confident that LLVM is going to let us build a JIT that will be competitive with our existing JIT. Remember, you get one shot at it. JIT time is super important. But for ahead of time or from install time, it might start to become really interesting. Or we might decide to build a tiered JIT architecture and actually allow methods to be rejitted. These are all things that we're thinking about listing. And maybe we'll be surprised and the performance will actually be pretty good. My initial ballpark is that the LLVM JIT is going to be about a factor of 4 slower at JITting than the Reed JIT. In code quality, we're not even really ready to talk about yet. There's the page. We actually just got our first pull request like an hour ago. Somebody fixing a bunch of typos in our documentation. Very helpful.
Sean Silva?
So what's that?
Nothing.
No, I don't know who it was. So we're using the MCJIT. We actually added some basic COF support. And I think David helped me get that checked back into LLVM. Our intention is to actually push everything that we do back. We don't really want to maintain a fork any longer than we have to. We've got a bunch of other stuff that we'll start pushing back. There's some discussion I already had about what we do about some specialized needs we have. Like, we don't really have the CRT there. Right now we're pretending like we're running against the CRT. So if we use a memcopy operation, something ultimately decides we want to call memcopy, we got a problem because there's no memcopy for us to use. But we have replacements for all these things. The JIT is multi-threaded. I haven't had any trouble. I've been using the thread local. Seems to have been working fine. So we basically have one LLVM context per thread, and they're all just sort of independent of one another. Seems to be working pretty well. We're doing a lot of modeling of CLR types using LLVM types. This is something that I might have to back off on, in part because we have some weird challenges of our own. The type system that we model in the IR is mapped onto a smaller set of types by the CLR in order to implement shared generic instantiations. We don't always know when this happens, and so this creates some type mismatches that we need to sort out. And then, you know, LLVM type system is relatively low level, and so there's just some things that are hard to describe. But it's my intention that the types be descriptive enough that we can use them to report GC pointers. So we'll have to see. Here's some sample IR. So there's a little piece of C# up there, more or less what it looks like. Name types, so we can see that string became system.string. We're using the address space 1 convention right now to sort of tag our GC pointers. So there's been some discussion about making that an attribute or something that we could tap into. And so basically, not super complicated. Now you'll notice there that in basic block number 2, we actually do an explicit test for null. So one of the challenges we have in translating MSIL is that MSIL operations generally can throw semantically meaningful exceptions, right? And so we need to manifest that somehow. Our natural inclination would just be to let the load instruction fault and then have some low-level handler up in the OS say, hey, wait a minute, I see what happened here. This is a null pointer exception. Manifest it back. For now, though, we're doing explicit checking everywhere. And we'll see where the discussions go with whether we can use invoke on loads and stores or things like that to decide do we want to go to a model where individual instructions can throw exceptions. But for now, we're avoiding it. It turns out this solves another headache with GC that I'll talk about a little later. But I don't know from a performance standpoint if we can sort of stick with this in the long run. Let's talk a little bit about the CoreCLR's GC. It's a generational GC. It's fully relocating, loves to move stuff around. Its desire in life is to move as much stuff as possible sometimes, I think. It's precise. It's a stop-the-world collector. Got a bunch of features. And there's places where we may have to support being interrupted at any point in the code. It's what we call fully interruptible. So that the thread might be suspended between 2 arbitrary instructions. The GC might demand to know where all of the GC references are on the frame at that exact point. And in some ways, you think, well, that might be terrible, but it's actually nice for things like loops. Because it's a stop-the-world collector, the JIT is responsible for making sure that the GC can grab control of the thread often enough. And so that might mean in a tight loop, you actually have to introduce a GC poll or something similar to give the GC a point to break in. You can do fully interruptible reporting, then it doesn't matter. Basically, any instruction the loop can be broken into. You don't have to do the explicit poll, kind of nice. But it's also more challenging in some ways. So those are some of the implications of this stuff. Since it's generational, we have to use write barriers to basically let the GC know we're going to do a cross-generational store. Because it's relocating, we have to imagine that when GC changes, every single GC reference changes values. Right? Because it's precise, we have to get the set of GC locations in the stack and registers exactly right. If we over-report or under-report, either way can lead to heap corruption, can lead to bugs. We have to be very careful sometimes where GC references are, especially if we're calling into code that's not itself GC aware, which is actually pretty common. We might be forced to spill all our GC references into safe locations, so we don't have to figure out how to decipher where they might be further up the stack. We have some weird cases where we have to keep locals live, even though they're not referenced anywhere in the method. I can talk more about why that is. And then we also might want to take advantage of what we call untracked references. So we'll get into this a little more, but the idea. So a bunch of challenges to getting this right. I talked about sometimes we have things that we can't have in registers. We need to report the kind. We need to make sure that nobody ever points off the end of an object. This is something that we're still kind of nervous about. We'll have to see, optimizers sometimes want to do funny things with pointers and point below or above arrays and things like that that streamline code gen. Pinning, which I'll talk more about in a second. Fully interruptible reporting, so reporting GC state points at every single instruction. Some things where now we can have GC state points inside of exception handling code. So how do we model that and get the semantics of that right? Making sure that callee saves don't contain GC references. Making sure that if a callee save is filled, it actually gets restored. I'll show you an example of this. Something that I screwed up once, so I would like to remind people about it. So this is all the stuff that we have to do in order to be correct. So here's an example of this. This is a bug that I introduced once in the previous compiler. Well, let's imagine we have some code where RBX has been spilled. We do a branch. On one of the branches we actually modified, on the other one we don't. And the other one has a GC save point. You know, look totally fine, no problem here. Then somebody says, well, let's tail duplicate the return. Once we tail duplicate the return, on one side we see the spill, modify, restore, everything's fine there. On the other side, well, we never modified this RBX, so why do we bother to restore it, right? Just a useless read of the same value that we had in there, okay? Now notice that RBX is not actually live at this point, but it turns out it's actually live into the GC. Because it might contain a GC reference, right? The caller might have put a GC reference in that register when it called us, and when we spilled it, it appeared on our stack frame. We have to report that, but it's not live for us. So there's sort of this complicated invariant at these save points that the spilled callee save state is also visible with GC. So we cannot optimize away this restore safely, because we might miss an update of RBX that happened if there was a GC there. Now, when I was working on this compiler, the guy that was having me do this said, he warned me about this exact bug. He said, don't make sure you do this, make sure you do this. I left it out. Sure enough, something broke. So it's not even hypothetical. It's happened to me.
Why did it have been updated in both places?
What do you mean in both places?
Well, in RBX and in the memory.
I'm not following in updated in RBX. In this method, we don't know what's in RBX, right? Here, we have no idea what the value is, right? We don't know if it's a GC reference or not. Only the caller knows that. So all we have to do is say where it is, and then it has to use the information from the caller to figure out whether or not it's something to be updated. So another thing that's tricky, this is sort of a puzzle for people writing compilers. We have this thing called pinning. So whenever you want to, say, pass a managed reference to some GC unaware code, you have to make sure that that thing doesn't move around. There's no way to go and find those references and fix them up. In C#, we do something like this. We'd say, okay, pin this thing using fixed, get its address, then pass its raw address to some native code or something like that. And it would do stuff, the object wouldn't move around, everybody would be fine. Well, we need to make sure that the scope of that pin extends just long enough to cover all the possible uses of it. Don't really want to extend it longer than that because it will hold on to stuff unnecessarily. We don't want to do it shorter than that because it might move unexpectedly. Try to get it exactly right. When you actually look at what this looks like in code, the constraint about where you can move it and the constraint about where it's used are just decoupled from one another. And there's no easy way to sort of say how far you can move uses of this thing before you get yourself into trouble. The rule is kind of complicated. It sort of says, well, you did this thing, and now you've got this blue variable. This is your dangerous variable, your pinned pointer. You can move uses of that around, but you can't move them too far. You can't move them below any sort of GC save point that would have reported the green guy, otherwise we're in trouble. So we generally don't know how to model this, and so for something like this, we'll often call out vol or something heavyweight seeming and say, like, there's just something weird going on here. Try to preserve this code as little as possible. Unfortunately, that means pinning sometimes has more overhead than you'd like. You'd like to think it should be free or very cheap, but sometimes it's not. So the other side of the coin from correctness is performance. There's a ton of stuff we have to do to get good performance. And so I talked a little bit about untracked reporting. The actual volume of GC info that we pre-produce for these methods can be pretty considerable. It takes up a lot of space in the address space. It has to be live in the process, right? The GC has to be able to consult it sort of arbitrarily. CLR does a ton of crazy encoding tricks to try to compact this stuff down. You'd like to defer a lot of this stuff if possible. So, trying to move all of this stuff to just before it needs to happen can be important. Particularly like one bad example is if you have a function that has a huge switch in it. Each of those switch has a lot of GC references, and you're not good at stack packing. What you might see is you come into the function and you immediately will zero, like, 100 slots on the stack. You'll take a branch, you'll execute like 4 instructions, and then you'll return. Like, well, why did I zero 100 slots on the stack if I was only going to touch a little piece of it? You like to be smart about where you pay for these things. We'd like to be able to model calls that can't cause GCs, but can cause side effects. That's a tricky thing for us to do now because when we report these things, it often makes it look like the locals have escaped, and so they seem to be modified by all calls, and be careful about that. There's some other stuff you can do. Null pointers don't need to be reported, so if you can do a little bit of range analysis or constant propagation or something, you can say, hey, I don't need to report this guy, no, it's null. And then some examples I'll do, right barrier optimization and safe point insertion. So for safe points, this is one of these classic things in a compiler where there's no good answer, and you just decide which answer is sort of least bad for you. If you put them in early, then you feel pretty good about yourself because you're sort of locking in the complicated semantics of GC. Hopefully downstream things have less opportunity to kind of mess with you and screw it up. On the other hand, it inhibits a bunch of optimizations that are actually perfectly fine, so you'd actually like to put them late to allow those optimizations to happen. But then there's some optimizations that sort of need to know that you're eventually going to put a safe point in there, so you'd like to have those happen kind of in between somewhere. So this is something we'll continue to work on, but for now we're just going to do early placement and try to get the code correct, and we'll worry about coming back to this as we sort of get smarter about things. For right barriers, a bunch of things you can do. Got a lot of text here. So if you know that an object has just been created and a GC hasn't happened yet, and you write to it, you don't need to report that to the GC because you know that this is in the newest generation. If you have to have a right barrier, you actually probably want to defer which version you call until you've done register allocation, and then do custom calling convention, because the right barrier typically is like 4 or 5 instructions, and so I force the register shuffle or do anything like that just for that. I think the CLR has like 16 versions you can call depending upon which register has which, so you'd like to be able to switch those around. If you got multiple writes close together in space, you can take advantage of the fact that the GC only tracks sort of contaminated parts of the old generation on a page granularity. So you'll actually need one write barrier per page per set of writes. So if you have like a memcopy loop that's copying a bunch of GC references, you can amortize the cost of the write barriers and just report them sort of sparsely. You can maybe defer that until after the entire loop and do a bulk report if you know no GC can interrupt your copy operation. If you store an all, well, you don't need to tell the GC about that either. And then the big thing, the thing that we used to do, and I don't know if it's feasible really in LLVM, is we would just have GC write barrier stores look like normal stores for a long time. And they basically just have an extra bit on them that says, I need to be a write barrier. And sometime later we would manifest that. But all the normal operations you can do, optimizations you've done to stores are fine for these guys. You don't want them to be excluded from sort of normal treatment. So you don't want to make them look too special until you actually have to. So as far as LLVM goes, as I said, it's been great to work with. The bugs we found have mostly all been ours. I seem to be particularly dense when it comes to insertion points for some reason. Like I was telling somebody, we have a lot of blocks that while we're creating the R, they don't have terminators yet, and so it's kind of awkward to be like, oh, is there an instruction there? Is there not an instruction there? It gets sorted out, but I don't know. Something about it, either my mental block or something there is just complicated in some way that I don't get. Not a big deal. Things that we've missed from other compilers, we talked about the exception thing. We had memory SSA before, we really liked it. It's complicated, but it makes it pretty nice to give sort of a uniform model. I hear it's in the works, or something is in the works.
Yeah, what
There's
kind
a
of
patch out.
Yeah, there is a patch out. What kind of SSA? The memory is one SSA value, or one?
It was optional. There was basically a set of models, right?
Okay.
You could decide,
Okay.
but there was a way to talk about it.
Right. It was just
Yeah.
which one were you hoping to get? It was kind of
So
the
we
question.
had basically a family of them, and you could sort of dial in how detailed of a model for memory you wanted, and it would sort of go from there.
Sure.
So,
I was just right now with the current patch just has one.
right. I mean, one might be enough. Like we need to say there's something in memory here that we need to pay attention to on this call.
Right.
That's what the current one is.
That's what the current one is. Yeah.
RIR in Phoenix had explicit notions of alias dependence. So we sort of had generalized notions of operands. So we had values. We also had other things that were sort of, they could have been values, but it didn't really matter what the value was. It just said this instruction produces something that this instruction sort of logically consumed, and so one has to happen after the other. This is nice sometimes when you do an optimization that creates an implicit dependence because you took advantage of some fact that isn't going to be true if you start moving things around too much. And so you want to constrain how far a particular thing can move. Like if I optimize away a null check because I had some higher thing up here that was sort of verifying that this thing wasn't null, I want to make sure that I don't ever move it above that thing and get myself in trouble anymore. We had pointer kind, so I know there was some discussion this morning about pointers and what happens to pointers. Obviously, we need to know where all the pointers are at all times. We can't lose track of them. Pointer gets converted into a non-pointer, then we're in trouble. I think with the early reporting of liveness, we'll probably be okay, but we haven't gotten far enough to be sure whether we're going to have trouble here. And then I've been talking to a couple people about this. We have this notion that the runtime artifacts have a nice abstract semantics, and it would be nice to sort of keep them that way for a while and then gradually expose what they are. Like an example might be a type test. So a type test might be, grab the V table, compare it to this other thing. If they're the same, you're good. If not, you got to go do something more complicated. Go call this helper function, blah, 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 blah. So if you actually expand it out early, it's very difficult to reason about what it is because somebody's got to go basically pattern match to say, is this the kind of stuff you got when you did type test? If you leave it abstract, something can reason about it. I talked some to Chris about it, and he's like, well, Swift has its own high-level IR. So I'm like, well, okay. That seems like, I guess that's fine, but honestly, I think there might be enough common operations like this that somebody could make a case that they sort of belong. Now, maybe they need to be intrinsics. I don't know, but there's enough of these, I think, that would sort of cross languages that it might make sense to have them be around as sort of general operations. So as far as status of the project, we are indeed open for business. If we look at what we're doing now in simple cases, I think we can handle, like just to JIT, a thing that prints hello world, you have to be able to get through something like 340 methods in the CoreCLR. And I think last I looked, we were at like 320. And a bunch of those that we couldn't handle were P and vote. The other thing we've been trying to do is been trying to run the Roslyn compiler against our stuff. On the Roslyn compiler, I think we can handle about 85% of the methods. So to get Roslyn to compile the hello world program, you get to be able to JIT around 8,500 methods, something like that. So, it's not complete. Like I said, we intentionally wanted to open it up early before it was kind of a finished thing. And so there's a lot of stuff still to do. GC, the CLR supports a conservative mode. I didn't talk about this in much detail, but conservative mode means the JIT really doesn't have much obligation at all. GC sort of looks at the stack and it says if it looks like a pointer into the heap, it is a pointer into the heap. It doesn't relocate anything, so it doesn't give you the same level of performance. But it's a nice way to sort of get started without having to solve all of the complicated GC problems right away. So we can sort of make progress on other fronts at the same time. EH we don't handle yet. Specifically, we cannot catch exceptions. So whatever test you run, it better not throw an exception because we won't catch it. And then we've also got a building working for a couple other platforms. So that's nice to see. We can sort of very quickly get that going. So some things that we'll probably talk about in the future for EH. We talked about that we'd like to have instructions be able to sort of raise semantically meaningful exceptions and have those participate in catches. We need to be able to push on the performance front. We're a couple months away from really thinking about that seriously. There's a lot of what we would call managed idioms, special patterns that you see in C#. One of the things I'm curious to see is how tightly tuned LLVM is to Clang versus just sort of some random guy generating IR. Our experience in the past has been that compilers become really habituated to their sort of primary IR producer, so we'll have to see what we run into there, but we'll find out. Probably the big thing that we'll think about is to build a true ahead-of-time system on top of all of this. So the JIT is really kind of a springboard into that. The idea is to get something that correctly describes the semantics of the code and then start working on it ahead of time. There's something that I think we'll put up on our site fairly soon that talks a little bit more about ahead of time and how it meshes with this existing thing we have that's called .NET Native and how they play together, how they interrelate. But the idea here would be that you could actually build your entire app into an executable that effectively kind of links in the pieces of the CoreCLR that it needs and leaves the rest behind. And then this thing could run without actually requiring the CLR itself to fire up. There's a lot of challenges with that. There's a lot of dynamic stuff that happens in the CLR. So like reflection in particular is challenging. Reflection in MIT would be like super challenging. But .NET Native will sort of show you a possible direction this can go in. And some of you, well, I probably shouldn't say anything about it. We've had some experience with, ahead of time, compilation of C# that hasn't made it into products, and so we hope to bring some of that expertise along as well. That's it. Any questions?
Type test, an example of what you have in mind?
As far as what the operation will look like?
Yeah.
Yeah, I mean, it would basically be something that took a value and some sort of description of a type. You know, I don't know exactly what that would be, and basically, if that value was exactly that type, it would either return true or it would cast the result to that type or whatever the thing would be. And if it wasn't, it would either throw an exception or return null depending upon the semantics of the particular operator. So, yeah.
I was going to say, or Chandler, one way you could deal with some of the higher level concepts that you want to do is you can turn them into calls or intrinsics,
Right.
and just have a custom language lowering pass that'll grab them at some more appropriate time that
Right.
you'd like to lower, as long as you'd like to do some cleanups and optimizations that, like, yeah, ignore these, assume that they're kind of black boxes that could do anything, and then you can.
Yeah, so for things that are sort of call-like in nature or
Okay.
eventually could expand into calls, then I think that
Right.
works pretty
Well, even something that can expand into diamond tests, diamond CFGs and stuff
Right.
like that for tests. You
Right.
can easily turn that into, lower it into a basic block test.
Yeah.
Got a question over there?
Yeah,
Can you debug the generated code?
you can. I have. So there's a debug reporting format that we emit that the CLR understands. And so that will allow you to just do regular debugging of this. We don't currently emit it, so right now debugging the generated code is a little harder. There's everybody familiar with WinDebug? It's the Windows system debugger, not So there's a plugin for that helps with generating or debugging managed code called SOS. And so if you use that, you can actually get a pretty good idea where you are in the code. But it's a little painful. But it'll get better probably in a week or two when we turn on location reporting and things like that.
Have you been following Philip Ream's work on precise GC?
Yes. Yeah.
Is it something like you've been following it well enough to contribute in any way? I think it would be particularly important that you guys work with Philip and like influence his work early.
Yeah. So I've talked
So
to
that
him.
it
I've
actually
talked to
meets
him a
your
couple
needs.
times. We're using his latest stuff. We fixed a couple bugs in it. So I think we're on the path to collaborating. And when I talked to him, it sounded like we were pretty much on the same page as far as where things wanted to go. We need some things that he wasn't planning on getting around doing, which I think will work out nicely. But yeah, it's the thing that we're building our stuff around. We have it sort of partially there. We have state point insertion going, as I showed, and we're starting to work through the reporting aspects. We need to translate the stack map format into our own crazy internal thing, so that's going to take us a little bit of time. Especially because, like I said, this thing is sort of highly encoded and compressed. But we should have that probably in a couple weeks. And then it's just a matter of sort of going through, there's an elaborate series of tests we can run to try to determine whether the JIT is correctly reporting GC references. We have these stress modes where we force the GC to interrupt as often as it can and move things as much as it possibly can in order to try to shake out bugs and reporting. And those are real painful to get through, but it's a lot better than, figuring out what caused the heap corruption that potentially happened long ago. So. Okay, yeah.
So using the multi-threaded LLVM context for NCG,
Yeah.
do you see any challenge for memory consumption? on this?
I wouldn't say we're real smart about memory right now. In fact, we were leaking memory like crazy. And I think I realized we should like delete some things that LLVM had allocated, and that fixed most of it. But I think we have to go through and do a better memory audit. One of the things we'd like to do, and maybe you guys can tell me if this is possible, is we'd like to force LLVM to always allocate memory into sort of a memory pool of our choosing. Like cordon off your memory, don't use the default CRT heap. It didn't look like there was a way to do it. I don't want to like override global operator new or something horrible like that. So anyways, we'll have to think about that. It's not a disaster to use a CRT heap, but you know, we don't want to leak. In fact, what we might need to do is periodically go in, even on the threads that are active, when we know we've reached sort of the bottom of the JIT stack, we might want to periodically go in and destroy the context and then sort of flush everything out, start over. Yeah.
I actually think it'd be good to spend some time. LLVM shouldn't be even perceived as leaking.
Right.
Whatever we're doing that looks like a leak,
Yeah.
we should go and fix.
Yeah.
The two places where this kind of happens today that it shouldn't is type construction, which is like it grows without bound.
Right.
There should be a way to go and kind of reclaim types and in a destructive manner, and there'd be some risks of doing that, but I think that would be healthy to have.
Yeah.
And some way forward. I think originally metadata was like that, but it's getting better now.
It's getting better.
Yeah.
That does remind me, one of the things that you might, I'm pretty sure the answer is that you're not going to be able to do it, but you're asking for ability to mark data in such a way for range checks and stuff like that.
Right.
As long as it's not going to, as long as stripping out that as long as stripping out that information isn't going to cause you to do something wrong,
Mhm.
you could attach metadata to it to provide some sort of information.
Right.
Otherwise, yeah, we'll need to come up with some sort of
Yeah.
IR level construct for it. Anything that can change, anything that would cause your program to not compile successfully
Right.
is something for an IR change. Otherwise, we can attach any
Yeah,
sort
so
of any sort of language specific metadata you'd like to attach to things to provide information down the line.
Right. Yeah, so I think we may be thinking about building some type hierarchy stuff.
That'd be interesting.
Yeah. You know, because like for type tests, if we sort of knew the inheritance path of this thing, we might be able to say, hey, we know you're of this type or something like that. We don't have multiple inheritance, but we do have interface, so there can be sort of a complicated
Right.
path you have to traverse. I was going to say something else, but now I forgot what it was.
Yeah, I know other people that have a tendency to destroy the context and restart at some point during JITting, and not a huge fan of that, so trying to figure out some way of it to prune that down and to fix that for
Right.
people. We have talked about, by the way, for even if it's not metadata on the context that's causing some problems, we can throw we've talked about moving metadata back to module. So.
Yeah, our modules are weird right now. They contain exactly one function, right?
So if you looked at the OrgJIT,
we looked at
I was going to say.
So a big open thing in there is how we're going to implement inlining. So we haven't done anything about inlining. The performance of this thing is going to suck until we do inlining, because if you know anything about .NET, the raw field accesses are pretty rare. Everybody goes through these property getters and setters, so every single field access looks like a method call, and the method is really tiny. It's like, you know, load this field and return. So we have some ideas about how we want to do it. We actually want to use the LLVM inliner. We don't want to build like a custom one that does some random thing. So that's something we'll probably get started on a month or two from now.
Yeah, one final question and then short answer. Maybe.
Sure.
Over there was a question? Or it's gone? Okay, then
No.
you can have it.
Well,
Chat
chat-
works
chat-
first.
Yeah.
So you seem to go into a lot of trouble to make the GC precise work. How much is it better than the conservative one? Wouldn't it just save you all the work?
I don't know that I can say definitively. We've done tests where the precise recording is 30 or 40% faster. So whether those are representative of real things or not. We have some bigger things. Once we get things working a little better, we can do some more realistic benchmarking. For now, it's a little bit tough to tell. But yeah, one of the things I was kind of expecting people to ask me is like, you know, why do you put up with all these crazy requirements? Why don't you just get them to change the GC? But you know, this is a GC that's been around for a long time, and it's been sort of carefully engineered.
So what makes the precise so much faster?
What makes it so much faster? I think because you're retaining a lot less stuff that you don't need to hold on to. So. GC tries to be careful, especially because it's relocating and can do things like try to optimize your working set and the density of sort of hot data on pages and things like that. If you hold on to stuff that you're never going to look at, then it sort of waters all that down.
So there are so many false positives. You just-
Because of the conservative, yeah. So,
And it wouldn't be a discussion of a managed language if people didn't ask about the pros and cons of various different GCs.
right, right. Yeah, so you can suggest to the CoreCLR guys that they allow experimentation with GC. Hopefully they say, sure, go for it.
Okay, thank you very much.
Thank you.